pretty mind-bending area where things you think you know, like information, reality, they get this quantum twist.
Uh-huh.
Let me start with a question for you. What if that really bizarre quantum world, the one that seems so tiny and far off, what if it's actually the thing shaping our everyday predictable reality?
That's a fantastic question to start with. It really gets you thinking, doesn't it?
Yeah.
And that's basically our mission today. We want to unravel this puzzle, this deep connection between quantum entanglement and decoherence. Because, people often talk about them separately.
Right, like two different weird things.
Exactly, but they're not. They're really two sides of the same quantum coin. So we're going to try and simplify this view, show how the apparent loss of quantumness isn't loss at all.
It's more like information moving somewhere else.
Precisely. It's a rerouting. And understanding this shows how our classical world, the solid world we see, actually emerges from these quantum foundations. And importantly, what it means for building things like quantum computers.
Oh. And yeah, our discussion today, it's based on insights from a pretty comprehensive report called Entanglement-Decoherence, a unified quantum perspective.
Okay, great. So let's start with entanglement. Everyone's heard spooky action at a distance, right? Einstein's phrase. It sounded almost, philosophical back then.
It really did. A paradox.
Yeah. So how did we get from that, from spooky to it being, well, absolutely central to modern physics and tech?
It's been quite a journey. So formally, entanglement means you have, say, two quantum particles, and they're linked. So deeply linked, they act as one system.
Even if they're miles apart.
Light years apart.
Or even light years apart. You measure one and you instantly know something about the other. It's like Schrödinger said he thought this was the defining trait of quantum mechanics. Knowing everything about the whole system, the pair, doesn't mean you know everything about the individual parts.
Which is totally different from classical thinking.
Completely different. Think about Bertelsmann's socks, the example people sometimes use.
Right, the pink and non-pink socks. If I pull out one pink sock from a box, I know the other one, wherever it is already not pink. It was always not pink.
Exactly. Or separating two gloves into boxes. One is right-handed, the other is left-handed. The properties were predetermined.
So that's just correlation. But entanglement.
Entanglement is fundamentally different. The properties like spin or polarization, they aren't fixed beforehand. They're sort of indefinite, a cloud of possibilities almost.
Until you look.
Until you measure one. The moment you do, its property becomes definite, and instantly, the partner particle's corresponding property is also fixed, no matter the distance. This is the spookiness that bothered Einstein.
And led to the famous EPR paper. Einstein, Podolsky, Rosen. They were arguing against this, right?
Yeah.
Saying there must be some hidden information we just don't know about yet.
They were. It was a brilliant challenge. But then came John Bell.
Bell's theorem.
Right. And the experiments that follow, they basically showed that entangled particles behave in ways that classical correlations, even with hidden variables, simply cannot explain. They violate Bell's inequality.
So reality check. Quantum mechanics is genuinely weird. No hidden classical tricks. Properties aren't fixed until measured.
That's the experimentally confirmed picture. And it leads us straight to the next point. This incredible power of entanglement, it makes it super fragile.
So the kind of entanglement we want to use, see, in a quantum computer.
That useful entanglement, yeah. It's very easily disturbed. It gets broken. Broken isn't quite the right word. It gets decohered by interacting with its surroundings, the environment.
Okay, so like friction turning useful motion into heat, the quantum connection seems to just fizzle out. But you said it transforms, not vanishes. Is that decoherence?
That's exactly it. The breaking isn't the end of the story. It's the beginning of a much bigger, more complex entanglement. The system particle starts getting entangled with particles in its environment.
And that's the process we call decoherence.
That is the process of decoherence.
Okay, so let's define decoherence more clearly then. It's the reason my coffee cup isn't hovering in a quantum fog of being here and also, I don't know, over there.
Hey, exactly. It enforces the classical world we experience.
So,
Fundamentally, it's the loss of quantum coherence.
coherence being the thing that allows for quantum weirdness, like superposition and interference.
Precisely. Think about the two-slit experiment. Particle goes through both slits, interferes with itself, creates a pattern.
The classic wave pattern.
Right. But if you try to find out which slit it went through, even a tiny interaction to get that which path information...
The pattern vanishes. You just get two clumps, like firing paintballs.
Exactly. Decoherence is like that which path information constantly leaking out all the time into the environment.
In this environment, It's not just empty space, is it? It's everything else.
Everything else. Air molecules bouncing off things, stray photons flying around, thermal vibrations in the table, even cosmic rays zipping through. It's a vast, complex quantum system itself.
So every tiny interaction is like a little peak, a continuous measurement.
Effectively, yes, a constant monitoring by the environment. Which naturally leads to the question, why do big things, like us or coffee cups, always seem to be in one definite state? Why not superpositions?
Yeah, why don't we see macroscopic quantum weirdness?
The answer seems to be something called environment-induced superselection, or einselection for short.
Ion selection.
Okay, the idea is the environment isn't just passive, it actively selects certain states. It favors states that are robust, stable against further entanglement. These are often called pointer states.
Pointer states, like the pointer on a measuring device showing a definite value.
Kind of. They're the states that survive interaction with the environment relatively unchanged in their definiteness. Think of it almost like quantum Darwinism.
Quantum Darwinism. Okay, I like that. So the fittest states survive the environment's scrutiny.
That's a great analogy. The most robust states survive and become the classical states we observe. Fragile superpositions get wiped out very, very quickly.
And for things like us, or my coffee cup, position is a key pointer state.
Absolutely. Imagine that cup trying to be in a superposition of two places. Environmental particles, air molecules, photons would scatter off it differently depending on which location it's in.
Ah, so that interaction immediately gives away which path information, destroying the superposition.
Instantly. The interaction entangles the cup's position with the state of those environmental particles, selecting for definite locations. Ein selection explains why our classical world has the structure it does, definite positions, momenta, etc.
Which brings us back to the core idea. Decoherence is this process of the system getting entangled with the environment.
Yes, that's the unified view.
But how does that work without some kind of magical collapse of the wave function? Doesn't something have to suddenly choose a state?
This is where it gets really counterintuitive but elegant. If you look at the total system or quantum system plus its environment.
The whole shebang.
The whole shebang.
Yeah.
From that global viewpoint, it's a closed system. And quantum mechanics tells us closed systems evolve unitarily.
Unitarily meaning smoothly, predictably, reversibly. No sudden jumps.
Exactly. Continuous evolution according to the Schrödinger equation. No information is lost from this global perspective. No collapse is needed. The coherence, the superposition, it just gets spread out into this vastly larger system plus environment state.
So wait, if there's no collapse, why does it look like there is? Why do I only see the coffee cup in one place?
Because you are a local observer. You don't have access to the entire state of the environment, all those trillions upon trillions of air molecules and photons.
Right, I can only see the cup.
And mathematically, what represents this limited view is an operation called the partial trace. You essentially average over or trace out all those environmental degrees of freedom you can't track.
Okay, let's trace this. Walk me through the steps.
Okay. Step 1. You start with your system, say a qubit, in a nice clean superposition, alpha up plus beta down. And it's separate from the environment.
Pure state.
Yeah.
Full quantum potential.
Right. Step 2. Interaction happens. The qubit interacts with particles in the environment. Now, the combined state becomes entangled. Maybe up gets correlated with environment state E up, and down gets correlated with a different state, E down.
But the total system is still pure.
Yeah.
Still evolving unitarily.
Still pure, still unitary, just more complex.
Yeah.
Alpha up, E up, plus beta down, E down. It's one big entangled state.
Okay. Then step 3, I, the local observer, come along. I can't see E up or E down.
So you perform the partial trace over E, you average away all that environmental information.
And what's left? What does my qubit look like?
What's left, mathematically, is a description of your qubit called a reduced density matrix.
Right.
And crucially, in that matrix, the terms representing the coherence, the quantum interference between up and down, they vanish. They average out to 0 because of the entanglement with the now ignored environment.
So the quantumness disappears from my local view.
Exactly. The qubit looks like it's in a mixed state, which means it looks mathematically identical to a classical situation where the qubit is either up with probability alpha squared or down with probability beta squared.
Just like flipping a classical coin. It appears as if a random choice was made. The born rule probabilities emerge naturally.
Precisely. That's the apparent collapse. It's an effective perspective of tracing out the environment, not a fundamental process in itself.
Wow. So decoherence isn't information loss, it's information spreading. The coherence isn't destroyed, it's just hidden in the correlations between the system and the environment.
It's delocalized. The mixedness you see locally is actually a measure of how much information, how much entanglement has leaked out into the environment.
That's quite a shift in perspective. Is this something we can actually, watch happen? Can we see entanglement moving around?
Amazingly, yes. There have been some incredibly clever experiments, especially using optics with photons.
How do they work?
Well, typically, they'll start with two entangled photons. Let's call them S1 and S2. These are the system qubits.
Yeah.
Then they deliberately send each of these photons through a separate decoherence channel, basically, a controlled environment, let's say E1 and E2, that interacts with the photon passing through it.
So you have S1 interacting with E1 and S2 interacting with E2.
Exactly. And the really neat part is they can then do what's called quantum state tomography on the whole thing, all four parts, S1, S2, E1, and E2.
Measuring everything to map out all the correlations.
Yes. They can track the entanglement between S1 and S2, but also between S1 and its environment E1, between S2 and E2, and even between the two environments E1 and E2.
And what do they see? Does the entanglement really move?
Unequivocally.
Yeah.
As the initial entanglement between S1 and S2 decays because of the interaction.
Which is decoherence happened to the S1, S2 system.
Right. As that happens, they see the entanglement between S1 and E1 and between S2 and E2 systematically grow. It's a direct, quantitative observation of entanglement being redistributed from the initial pair into system-environment correlations.
It's literally watching the information leak into the environment's correlations.
So that's exactly what it is.
And does this framework explain some of those other weird entanglement effects, like entanglement and sudden death?
It does, perfectly. ESD, entanglement sudden death, sounds dramatic, right?
Yeah, it sounds like it just vanishes abruptly.
But in this picture, it's not vanishing. It's when the initial entanglement between, say, S1 and S2 has been completely transferred into other correlations, S1, E1, S2, E2, maybe even E1, E2. From the S1, S2 perspective, the entanglement is zero. It's dead, but globally, it's just rearranged.
Okay, that makes more sense than just popping out of existence. What about the opposite? Can it come back?
Sometimes, yes. That's called entanglement sudden birth or revival. The overall evolution is unitary, remember. It's reversible in principle. So the dynamics can sometimes cause entanglement to flow back from the environment into the S1, S2 system.
Wow. So it can die and then spontaneously reappear later.
Under the right conditions, yes. It strongly supports this idea of entanglement as a kind of resource, a quantity that flows and redistributes within the larger system rather than being fragile and easily destroyed. It just gets harder to access locally when it leaks into the environment.
Okay, so putting this all together, what are the big takeaways for how we understand reality and for actually building quantum stuff?
Well, for understanding reality, this unified view really clarifies the quantum to classical transition. Decoherence, through inselection, explains why we see definite classical states the preferred basis.
Like position for big objects.
Right. And the partial trace mechanism explains how we get classical probabilities, the appearance of randomness and the Born rule emerging from underlying quantum superposition just by ignoring the environment.
But it doesn't quite solve the measurement problem entirely, does it? It doesn't explain why my specific experience is of this outcome, not the other branches that decohered.
That's the crucial point. Decoherence explains why the branches stop interfering, why they become effectively separate classical worlds, but it doesn't explain why we seem to experience only one of them.
So it transforms the problem.
Exactly. The question isn't why does the wave function collapse anymore? It becomes, given this universal wave function that's constantly branching due to entanglement with the environment, how do we interpret that? Why does our consciousness follow just one branch?
Which kind of provides the physical underpinning for interpretations like many worlds.
It gives many worlds and other interpretations a concrete physical mechanism for why the worlds separate and stop interacting. It makes those interpretations much more grounded in physics.
Okay, now the practical side. Quantum computers. This whole process sounds like the enemy.
It is. It's the absolute bane of quantum computing. The very process that makes our world stable and classical is what destroys quantum computations.
Because quantum algorithms need that coherence, that carefully controlled entanglement.
They rely on it. Decoherence is just uncontrolled, messy entanglement with the environment. It leaks the quantum information out, randomizes the phases. Basically, it introduces errors and kills the computation.
Which is why current quantum computers are called NISQ, noisy intermediate scale quantum.
Exactly. They're powerful, but noisy means they're constantly fighting decoherence. It's a race against time to finish the computation before the noise overwhelms it.
So how do we fight back? If perfect isolation is impossible.
We have to get clever. We use quantum error correction, QEC.
QEC.
The idea is, instead of trying to prevent errors perfectly, you encode the information redundantly and actively correct errors when they happen.
How did that work?
You encode a single logical qubit, the information you care about, across many physical qubits using complex entangled states.
So you spread the information out.
You spread it out in a very specific, clever way. Then you perform special measurements called syndrome measurements. These tell you what kind of error occurred and where, but crucially, without revealing the actual logical information stored.
Ah, so you diagnose the problem without destroying the data.
Precisely. And once you know the error syndrome, you can apply corrective operations to fix it.
It sounds like you're using entanglement to fight entanglement.
That's a perfect way to put it. QEC is like engineered recoherence. You use controlled entanglement and measurements to detect and undo the effects of the uncontrolled entanglement caused by decoherence. It's fighting quantum fire with quantum fire.
And that's the hope for building large-scale, fault-tolerant quantum computers.
It's considered the most promising, really the essential path forward.
This has been incredibly insightful, so let's just quickly recap the main thread here.
Please.
Decoherence and entanglement, not separate things. Decoherence is the process of entanglement forming between a system and its environment.
Two facets of the same quantum interaction.
And the apparent collapse or loss of quantumness locally is just the information, the coherence, spreading out into that bigger system, becoming inaccessible to us.
Right, delocalized into system-environment correlations.
Which means our solid classical world isn't fundamental, it's emergent. It appears because quantum systems are constantly interacting, constantly leaking information via entanglement with everything around them.
Classicality as an emergent feature of open quantum systems. That's the modern understanding. And it's not just philosophically interesting, it's vital for building quantum tech. Our ability to control or even reverse this process is key.
Absolutely. Okay, time for our final thought. If our everyday reality, the world we perceive, is really just a slice of the universe that has decohered for us, constantly shaped by information leaking into an environment we can't fully access, what deeper truths, what other aspects of reality might still be out there hidden in those correlations, forever entangled just beyond the reach of our direct observation?
A profound thought to end on. What remains hidden in the unobserved universe?
Something to ponder. Thanks for joining us on The Deep Dive.